You are working to fund a new freezer. Tell us about this technology. Can't you just go to, I don't know, Lowe's or Best Buy and buy a freezer? Isn't that sounds pretty easy?
Those compressors have been running for 25 years. We built the freezers in 1990, and now they're close to the end of their lifespan. And one of the rooms has
structural problems.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff. With departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others, the college always has something exciting happening. Join us to find out what's new now.
I'm so pleased to be joined today by Lonnie Thompson and Ellen Mosley-Thompson, who are among the world's most renowned paleoclimatologists. And that's about as brief an introduction as I dare muster for the two of you. Doctors Thompson, welcome to Voices.
Thank you.
Great to be here.
So I describe you as paleoclimatologists, and I'm curious, well, I suppose, first of all, a definition of paleoclimatology, but when you were starting off as graduate students back in the day, was there such a thing as paleoclimatology, or did you invent this field?
We certainly did not invent it. It was there. I think it's gotten more focused over the years on the paleo records, and particularly glaciology and getting paleoclimate records out of glaciers was just getting started when we were graduate students. So we were very fortunate to know all the pioneers in this field and to work with them. But still, when we were starting, the idea that you would become a glaciologist and actually get a job was remote because there were very few universities that actually had a glaciology faculty position.
When I came, I entered the Department of Geography's Atmospheric Science program. And I had done my bachelor's degree at Marshall University in physics and math. And so I was always enamored with climate and atmospheric science, had a fellowship, and I applied for it. And so I got my master's and PhD there. It was then called the Institute of Polar Studies years ago. Then it became the Bird Polar Research Center. And then we realized we were conducting, most of the research we were conducting was related to climate and climate change. So we changed our name to Bird Polar and Climate Research Center. And it was our activities in that center that really helped us get focused on the use of ice cores to extract past histories for Earth's climate system.
Yeah, say a little more about the method, about how you work with ice cores.
Well, first of all, let me say that even after 50 years, ice cores are amazing. And they're probably the best recorder we have of climate, not just temperature of the planet through isotopes, accumulation, precipitation. Very few archives allow us to reconstruct how precipitation has changed. But they also record history of things that cause climate to change. Volcanic eruptions, tephra and sulfate layers in cores. There's a history of the output of the sun, which is most important for driving climate on this planet. We measure cosmogenic nuclides, beryllium-10, chlorine-36. And there's a history, and probably best known history is the history of the gases in our atmosphere trapped in the bubbles in the ice that now in the polar regions span the last 800,000 years. So they really give us a perspective on where we are today and where we're likely to be in the future.
How has precipitation changed over time?
Well, precipitation has changed, and we go through long periods of lower precipitation and higher, and it's amazing working with archaeologists and anthropologists in South America to be able to really link the rise and fall of those agrarian cultures to changes in precipitation. So, we've always been dependent on climate on this planet, temperature and precipitation. And, of course, that's one of the things we're worried about going forward because these things are changing everywhere.
Ellen, you said back in graduate school you were interested in climate. And I wanted to ask both of you, what drew you to this field? Did you know when you went to graduate school you were going to study climate or you were going to study glaciers?
No, not at all. But it was the opportunity that the now Bird Polar and Climate Research Center offered, the opportunities to go into the field, in other words, to places like Antarctica or Greenland, or in Lonnie's case, particularly the high mountain glaciers in Peru, where he's gone for so many years, and the glaciers on the Tibetan Plateau. No, there was just a real excitement at the time. The center actually was instituted or declared to be an institute by the president of Ohio State right after the International Geophysical Year. And so that was like 57 and
57, I think, yeah.
58. And there was just a general excitement about the opportunity to learn about places that not many people had the opportunity to go. In the 60s, they had just drilled 2 deep ice cores, deep meaning they drilled to bedrock, and at 2 places, one in Greenland, one in Antarctica. And there were a lot of analyses going on, and it was just a really exciting time.
I came to Ohio State to study coal geology because I grew up in West Virginia, and I was looking to get a job when I finished my graduate studies. And frankly, when I first was offered a position in the Institute of Polar Studies to study ice, I didn't see how you could make a living studying ice. But I took it because it was a research position and you could get your degree faster. And it took a couple years to start to realize what might be possible in these archives.
I was a young professor. This was probably around 1994. And I first started teaching my students about climate change, which for me was this new and revelatory thing. When did scientists, I think, start talking about climate change?
Well, the discussion of climate change goes back to the middle of the 19th century.
Oh, wow.
Oh, yes.
So I was late to the game.
Well, but it was the basics of climate change. That's when several people, I don't need to go into the names, demonstrated that water vapor and carbon dioxide in the atmosphere would warm up and then emit long-wave radiation. And that's how they came up with this concept of, they call it the greenhouse effect. It's not really a greenhouse effect, but it's something that people can remember. But those people worked, in the 1850s, 1860s, and that was the first demonstration, actual experiments that demonstrated, yes, these gases do interfere with the radiation, the long-wave radiation. And then more people joined in. They started looking at climate variability, a relationship to the sun, how much radiation the sun puts out, the way the Earth orbits the sun, when its tilt changes, when its orbit changes. They realized that impacted climate. So there was a lot of activity on climate change. The big difference was when it was generally accepted that human activities are sufficient to modify the natural variability of the climate system.
I think it's important to point out in the 1970s when we were getting our degrees, there were discussions of the coming ice age. There were actually workshops on this. So the idea that climate change, yes, but natural variability was a bigger factor at that time. And I think it's also important that when we started looking at glaciers around the world, we didn't do that to study climate change. We did that to try to understand how a low latitude, a tropical glacier, behaves relative to the ones in the polar regions. It was just basic glaciology, understanding the system. And it was only with time that we started to observe the changes that were taking place. And I can pinpoint the year. 1991 was when I became convinced we had a problem, because that year was the first time I observed melting on the summit of the Calcaya ice cap, in this 18,600-foot ice cap in the Andes in Peru. And I started working there in 1974. And it was in 1992 that I first testified before the U.S. Senate, along with other paleoclimatologists, about our concern of what was happening in these remote parts of the planet. as far as the warming taking place. And unfortunately, since that time, it's only accelerated.
So you study ice cores. This is how we sort of study this. Give us a description of one of these ice cores. Are we talking about something that's, 10 feet? What's the size? What's the scale of these ice cores?
The size of them depends on the length of the drill. If you're drilling in Antarctica, you have cores that are 6, 8, 9 meters in length that come out of the barrel. They're about 10 centimeters in diameter. But we cut them into 1 meter lengths so that we can get them in tubes and we can get them stored in our freezers and the like. But the length of the core initially depends on the size of the drill that you're using. And if you're going to drill through Antarctica, you need to bring up lots of core each run, because as you get deeper and deeper, and that ice sheet's 3,500 meters, you spend more of your time going up and down the borehole than actually drilling down at the bottom when you get down to depth. So it's, it may take 5 years to drill through Antarctica. Our mountaintop glaciers are not as thick, and we can usually do that drilling in one season, 2 or 3 months.
Yep. So essentially, as Lonnie said, we cut them, they come up, and we record the stratigraphy. Anything, we measure the length, we measure the diameter, we make a recording of the stratigraphy. Anything that is visible that we can see. Are the size of the bubbles changing, their shape changing? Do we see particulate matter? Like Lonnie mentioned, the volcanic eruptions. If the site, like that particular location, is close to a volcano, then you'll have visible volcanic horizons. But actually, there are many, many more, but you don't know about those till you get back to the laboratory and measure like the sulfate concentration. Then you can see how rich the history of volcanism is in the ice cores. So we make a stratigraphic recording, then we put the core in a plastic sheath. We do all the marking so that, where was it drilled, all of that information. Then we put it in these tubes, these silver-coated tubes, and then we have special boxes. They're blown foam, very thick foam, and we put 6 of the tubes in the box along with some what we call cryopack material that we freeze in the field and then put it in the box. Then we start worrying about how in the world are we going to get it home, and the answer to that
My next question.
The answer to that is, where are you? Where was it drilled? Because So, for example, Lonnie has a lot of experience with yaks because if you're drilling in Tibet and you need to bring the ice down, you'll use yaks, you might use horses.
No SUVs or anything like that.
No, not that. But I work in Antarctica and Greenland, and there we have the capability of having aircraft that come in and pick up the ice. Then we can very quickly get it into a freezer, like in Antarctica or in Greenland, and wait for a military flight that brings it in to the States. So I have a very easy job, not easy in the field
Relatively
collecting
easy.
it, but getting it back for people working in the polar regions is much, much easier than trying to get it back from 18 to 22,000 feet in mountainous areas, rural mountainous areas.
We both mentioned freezers, and I know that you are working to fund a new freezer. Tell us about this technology. Can't you just go to, Lowe's or Best Buy and buy a freezer? Sounds pretty easy.
No, these are walk-in freezers. We have a lot of commercial use of freezers. They're built for storing lobster and steak, so there's a lot of commercial use. We just adapt that technology to storing of ice core. We need temperatures of minus 30 degrees Fahrenheit, and we need to have the special shelvings for the cores inside. And then, of course, all the vertical and the horizontal bandsaws and things we need to process the cores under cold conditions. You have cold storage rooms where you keep the temperatures really cold. That's where you keep your archive. And then you have work rooms which are warmer, where people can actually spend hours cutting and examining the core before it's taken into the various labs.
Mm-hmm. The reason we can't use something from Lowe's, of course, is obvious. They don't have the minus 30 Fahrenheit capability, but it's really the volume of ice. We have 2 very large freezers that are absolutely full of ice that's been collected over the last 40 plus years. I think the estimate is about 7,000 meters of core?
Close to that, yes. We have the most geographically diverse collection of ice on Earth because we have ice that comes from glaciers that no longer exist. We have the largest collection of ice out of Tibet in the Western Hemisphere. We have ice out of Franz Josef Land up in the Russian Arctic. And, the world is full of windows, political windows that open and close. And there was a 3-year period when the Soviet Union fell and before the current Russian government got established that we were able to get into the Russian Arctic, drill our ice cores, get them out of there. And the place is now closed again. It was closed 30 years before, and who knows how long before it opens again. But we have those cores, an archive of that, in the freezers downstairs.
One of the most unique cores we have are from Mount Kilimanjaro.
Drilling ice cores takes a diverse skill set.
Imagine.
Because you have to be able to work with people. I mean, we've been very fortunate. We've worked in 16 different countries in addition to Antarctica and Greenland. That means you have to have international collaboration. You have to have trust. And those cores from Kilimanjaro, we drilled them in 2000. There have been other groups who've tried 3 times to repeat what we did, and they have not been successful. And it really does come down working with people and having the trust of those people.
And the ice fields on Kilimanjaro are essentially melting. I mean, they're shrinking laterally, they're shrinking vertically, and there will be a time in the not too distant future. Nobody can actually predict when will the last sliver of ice on Kilimanjaro melt, but it is coming, and the only cores from Kilimanjaro will be in the Ohio State University's freezers.
You called these walk-in freezers. Give me a sense of the size. I mean, sort of size of a room or maybe a small building or...
This room here would be about the size a little bit smaller than our largest cutting room. That's just the room Lonnie described where the temperatures are just maybe 4 or 5 degrees below freezing. That's where the samples come out. They're cut, cleaned before they go into the laboratories. And we have 3 of those. And then behind those are 2 very large freezers that would be, what would you say, 6, 7 times this size?
Yeah, maybe.
Yeah, the room we're in is probably about 10 feet by 8 feet, if I were guessing.
Each one of those is what, about
500,
500 square feet. 2 freezers of 500 square feet. Then we have a third box. We call it the do not freeze room, where we had been storing sediment cores that were drilled in the Arctic, most of them in the Russian Arctic, by a colleague who has since retired. And those cores have now been shipped to Oregon State, where they're accumulating most of the ocean cores that U.S. investigators have drilled.
In our expansion and renovation project, we have 2 stages. One of the stages is to renovate the rooms we currently have, because those compressors have been running for 25 years. I mean, we built the freezers in 1990, and now they're close to the end of their lifespan. And one of the rooms has
Structural problems
and cannot really be fixed. But we're hoping to renovate that sediment lab, since it has nothing, and put in a freezer within that system and be able to expand on the short term.
As Lonnie said, the sediment room, make it into a freezer, change it over, and take the cores out of the second room, which is the one that has structural problems, move that out and totally rebuild that second freezer. We hope to go to a new location.
Yeah. We have big issue right now is space. We don't have space for new cores, and we just submitted a proposal to drill 1,000 meters, and we really don't know where we're going to store it because Our freezers are full, the aisles are full. We have cores stacked in those freezers. So initial stage to give us a little more room so we can expand, get the cores properly stored. But the longer term goal is to build a new research building here on West Campus, and the new freezers will be in there. So we have a short-term goal, maintain, sustain this collection, and this is really something we're doing for the next generation of ice core people, because we can keep these going for finishing our career. But when it fails, could be any time.
Well, and you describe this as an archive, and it is an archive, and part of an archive is not just simply preserving, but preserving for, well, presumably forever. In an archive that I would work in as an historian, the implication is that a document is preserved today and will be there 500 years from now. This is the goal with ice cores, I'm guessing.
And it's really important because 8 of the glaciers around the world where we've drilled, those glaciers now have a water table in them. They're melting at the top, and the record is being altered and in many cases lost. But we know just in the last 10 years, new technologies, we have a major program right now looking at microbes, looking at bacteria and viruses stored in the ice. And the beauty of that, we have a time series, and we can look at things like evolution. How do viruses and bacteria behave as we go from warm climates to cold climates? And more importantly, how they're going to behave in this warmer world we're going into. Well, the ice preserves that. But the technology to actually examine that didn't exist 10 years ago. And so we are using that, working with our colleagues over in microbiology department. We share postdoc, and we are now just publishing our very first breakthrough papers on this. I think it has a huge potential. We are now measuring things like black carbon. Black carbon comes from fires, and because you have an annual history, and we have ice cores from the top of the Andes, right above the Amazon. The big question is, hey, we know what the fire history in the Amazon has been since we've had satellites, but what's the fire history over the last 30,000 years? Well, we can address that using this archive. And again, these measurements weren't possible 10 years ago.
And there's an aspect to this, that is, there will be more technological development coming along. And if we use up all the ice right now with the technology we have, we would not be able to take advantage of the newest technology as it comes along, because we won't have any ice. So, it's really important that we keep this archive essentially alive for, as Lonnie said, the next generation of
20 years
scientists.
from now, you can just imagine what might be possible in a non-destructive way to extract out of the ice. But you have to have the archive.
In the way that archaeologists can do radar without actually digging up the land, they can still see what's underneath.
Exactly. So I believe that technology will continue to develop, and new ideas. When we started 50 years ago, we never thought about bacteria and viruses. I mean, we were measuring dust. That was the only thing. And now we measure 15 different parameters on those cores. And these new things keep coming online. And
the new mass spectrometers can measure 70 and 80 different elements out of one sample.
How do you do that? How do you make decisions today without really a clear sense of what the technologies are going to be 20 or 30 years from now?
Well, we have certain samples like those from Kilimanjaro. I mean, we have tried to accommodate requests from other labs around the world for samples, but when the sample archive gets to a certain size, we just shut it down because some of these techniques require huge amounts of sample volume. But I know in 20 years they won't, because they keep making these techniques more precise, requiring less material. But we try to do the maximum science we can do now using the archive, because our funding requires that we have publications and show new breakthroughs in science. But at the same time, you have to keep your eye on the future and make sure there's a preservation of that archive, because we won't have a chance in the future to get these cores. So we will lose all the mountain glaciers, no matter what happens going forward, because there's a lag in the climate system, and we will continue to warm for the next 20, 25 years, and that will be the death to most of our mountain glaciers and these archives. And even if the world gets colder in the future, history will start anew. That old history will be gone.
You're raising money right now for this new freezer?
We are. We have Buckeye Ice here at the Bird Center, and you can log on to the Bird Center and make a donation to that, and it goes for the renovation. We also have a fund down at the Columbus Foundation. It's called Canary, Ice Core and Educational Fund, and it comes from the fact that last year we released a new documentary on the research that we do here that premiered in New York and is now streaming on Amazon Prime, Apple TV, and it's called Canary because it goes back to when I grew up in West Virginia and the miners taking the canary down into the mine and watching the canary as an indicator of what was happening to the atmosphere. And so the analogy is the canary told the miner to get out of the mine when it died, and our glaciers are our canaries telling us we have to do something about climate change.
Yeah. Where are we right now as a planet, as a species? What are we doing about addressing climate change? Are you satisfied, dissatisfied?
Well, no, we're not satisfied, of course. But what's being done varies across the planet. For example, the European countries are far ahead of the U.S. in terms of how they're trying to either not emit more greenhouse gases, let's just say, call it carbon dioxide, methane, and water vapor are the three important greenhouse gases. And they're all tied together. They're working on more efficient equipment. They're working on extracting the carbon dioxide, let's say, out of the atmosphere and put it somewhere that it can be stored. The U.S. is doing that as well, but kind of doing it on the fringe. In other words, it's not a major thrust in terms of the U.S. People hear, drill, baby, drill. Yeah, well, that's not helpful in that regard. Now, you can go and discuss the economics of it, but no, we're not anywhere near where we need to be.
To me, the greatest concern is the rapid rise in temperatures on this planet. The last 50 years have just been astonishing how rapidly and continuous temperatures rise. And the number of extreme weather events, it's almost nightly now, and it's global. We pay attention to things here in the U.S., but it's around the world. And if you look at from July of 2023 to this past September, every one of those months were record temperatures for the planet. And one of them, last September, the temperatures were 0.5 degrees C warmer than any other monthly temperature. And we don't understand why. I mean, our models cannot account for such a strong warming. And one of the fears is that we may be losing control of this system because there are tipping points in our climate system, things like the Amazon basin. As we warm the planet, those systems are, in the case of the Amazons, drying up. The permafrost is melting and it's releasing more greenhouse gas, natural sources of greenhouse gases. So people are concerned that we may be approaching tipping points on some of these big systems on our planet. And when you cross those, you're no longer in control. It wouldn't matter what we as humans do. So we don't know a lot about tipping points, if and when we may cross those boundaries. But I think when you see things happening that you cannot explain in the recent rise in temperatures, you certainly have to be concerned. The glaciers, to me, they tell the truth. And they tell the truth because they have no political agenda. You cannot lobby them. You cannot have special interest groups. They're just summing up their temperature, precipitation, humidities, radiation, everything that affects them, and they're responding. And they're all responding in the same way around this planet. They're not only retreating, they're accelerating in their rates of retreat. And of course, this creates huge water issues for people in many parts of the world. In the Andes, I just came back from a workshop in Paris on the Himalayas, because there are 2 billion people who are going to be impacted by the loss of water resources as these glaciers continue to shrink. So, yeah, glaciers don't care what we think, and this is one of the beauties of being a scientist. I mean, it's really about geology and physics and chemistry, and it will continue. And I can tell you the next hurricane that comes, it's not going to knock on your door and ask you whether you're a Republican or a Democrat. Your house is going to be gone. And that's the way nature works. I think, yeah, they are really studying glaciers, watching them is a way to really get truth of what's happening to our climate system.
In terms of like the September warming, etc., we do know what's happening. In general, it's the increased concentration of these greenhouse gases that have the warming underway, but it's then the feedbacks that we don't understand as well and that we can't model as well. He's talking about like the melting of the permafrost, raising sea level, for example. All of these things are feedbacks, because what they do is they take the initial action, which was this slow until about 1950 increase in carbon dioxide, particularly in 1950. Post-World War II, everybody wants a car, everybody wants a house, and we start building suburbs, and greenhouse gases go up. You plot the temperature, you plot the greenhouse gases, and they plot in lockstep. But at some point, then we get those feedbacks, and they accelerate that initial forcing, which was the release of primarily CO2, carbon dioxide, but to a lesser extent methane as well. And there's the issue of water vapor. I'm teaching an honors course right now on global climate change, and I always ask the students on the first day, what do you think is the most important greenhouse gas? And they'll say, carbon dioxide. No, the answer is water vapor.
Oh, I would have said methane, but...
Yeah, well, it's water vapor, because these gases, the CO2, we measure in parts per million, methane is parts per billion. We measure water vapor in percent. Water vapor is a slave to temperature. If things warm, you have more evaporation. So then they have more greenhouse gas, you have more water vapor, and that warms the planet. It's these positive feedbacks that have put us in the current situation. And those are what we don't know well, and that many of which are out of control.
I would say that there's always been natural variability in the systems. Things like El Niños. El Niños are warm years for the planet, and we've just come through an El Niño, so we expected temperatures to rise a certain amount based on previous events. But the rise over the last year has just been unexplainable based on our current knowledge of the system.
That's where the concern about tipping points comes in. Yeah. You just don't know where you're actually going to tip.
This is the end of part 1 of my interview with Ellen Mosley-Thompson and Lonnie Thompson. Please visit go.osu.edu/voices for part 2 of this interview. Or better yet, if you're subscribed, you'll get the episode delivered. More information about subscribing is also available at go.osu.edu/voices.
Voices of Excellence is produced and recorded at the Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Produced by Doug Dengler. I'm Jen Farmer.